However, if we have something that has a deadline, here you see now we see that we have a latency to the deadline of 800 for the disk here, and it takes service time. So the most we can delay in starting running the disk thing is 300 milliseconds. The trouble is that you can see that the service times of both the keyboard and the printer are longer than the maximum delay that's possible for the disk in order for it to meet its 800 microsecond deadline. So now what we're going to do is say, okay, we finally have to face facts. We're going to have to interrupt what's going on. We're going to have to stop what we're doing and simply service the high priority thing. And this makes sense, right? We're going to have to stop playing the Bejeweled game in the back seat, even if we started, running it for a little bit. We're servicing, the button press handler. We're going to stop that, and we're going to deploy the airbag, okay, in response to this very short deadline. So to actually instantaneously deal with the thing that has the earliest deadline, you have to stop what you're in the middle of and go off and simply service the higher priority item. And that's called a strong priority system. A strong system has preemptive interrupts. Higher priority things preempt the running of lower priority things. Did you sort of get the basic idea? So there's preemption, which is our best shot at getting the handlers run before the deadlines. There's a weak priority system, which is a little easier to build. It involves less hardware, but the latency guarantees are not as good. And then finally, there's the, I'll just do anything in any order system, which is sort of what we have until we introduce this notion of priorities at all, in which case the latencies are even worse. So what we've done is go through a successive set of steps trying to improve the latencies. And this strong system actually has the best possible response that we can come up with. Okay, so now we get to the observation earlier. If we give the disk the highest priority, its latency is essentially 0 because it will preempt anything else that's happening on the system. The keyboard, how long is it before we service a keyboard interrupt? Well, if there was a disk interrupt at the same time, we'd have to service that first. It has higher priority. So now the latency before servicing, the printer, how long do we have to wait to service the printer? We have to wait for the disk to finish. So the service time of the higher priority things are getting in the way of the latencies of the lower priority things. So in this case, we have to wait 500 for the disk to finish, and now the printer will run immediately afterwards. And finally, the keyboard has to wait for both guys. So the strong priority system is you can adjust the priorities, and you can determine quite exactly what the latencies are. And you can fool with the priorities until you get the latencies that you want. Okay. So how do you implement strong priority system? Well, you probably have to replace, the status up here, which used to be just sort of user mode and kernel mode. It's not only user mode and kernel mode, but there's also additional information about the priority you're currently running at. And a device that interrupts, like the disk, not only has to say, I need your help, but then it comes with an associated priority. And if the incoming interrupt request has a higher priority than the priority that you're running at, okay, then you would then you take the interrupt. So the interrupt hardware now is slightly more complicated. It's not just are we in user or supervisor mode. Okay, it's also what's the priority of the current interrupt compared to the request interrupt compared to what we're currently doing. And it might be another interrupt handler. Okay, we might be in the middle of doing the printer, but the disk interrupt will say, I'm priority 3, you're only 2, so my turn. And so the hardware would then jump to the disk handler. Everybody sort of get this notion of strong, weak, and nothing. Okay. Okay, now it's sort of interesting to figure out this is a fascinating diagram, and this is sort of what happens in real life. If you think about the implications of a strong priority system, you realize that if you have recurring interrupts, for example, here we have disk interrupts happening 500 times a second, and print interrupts happening 1,000 times a second. So you can see the printer here is we get requests from it a lot. It's being very pesky. The disk, which has the highest priority, which means whenever there's an interrupt, it gets to run. Okay, it happens occasionally, and sort of what time is left goes to the keyboard. So the amount of we actually have to take into account when calculating the keyboard's latency, not only how long the disk in the printer would take once, but if they happen to reoccur before we finish processing the keyboard, they'll take another chunk out of the keyboard's time. And you can see this poor yellow stripe here. This keyboard guy, his execution is spread out over many interrupts from the keyboard and the printer. Right, so the actual time until the keyboard finishes is complicated by the fact that higher priority things may get several requests in during the long service time of the keyboard. So it actually turns out the accounting you have to do gets somewhat complicated by all these extra recurring interrupts that happen. And in a real-time system, that's what you have to worry about that. I mean, the notion that things like the carburation system aren't happy with a single interrupt. They'll need to be serviced, quite frequently to keep the engine mix correct. Yes?
On the previous slide, it said that strong priorities allow preemption but not re-entrance.
Right. So what that would mean is that once I'm running, so each device gets a certain priority. But once you're running at a priority, the disk can't interrupt itself. If you got devices that are at the same priority level won't preempt each other. So if you're in the middle of a disk interrupt handler, you would never get another disk interrupt. So you're never going to be re-entering the same code. You might be interrupting some code that you're running and running some different code, right? But you don't have to worry about the code that you're running being preempted. So that probably means you have different user blocks for each priority level, because you may be in the middle of saving the registers into the priority 2 block when you get a priority 3 interrupt. Well, it can't use the same user block because you haven't finished saving it. So you probably have to have a special block for each priority level so that you can save the registers, and when you return, you'll go back to saving the registers in priority 2, right? So the structures get a little bit more complicated, but the basic idea is pretty simple. Some of the engineering needs a little working out. Okay. So you can actually ask yourself, well, is there any time to do anything but service interrupts? And so you can start calculating what percentage of time each device is taking. How long the service time is, plus, multiplied by how many times a second it happens will give you a sense of what percentage of the CPU is running. Of course, if there's no time left, the kid in the back seat is going, my Bejeweled game isn't working too well. Right? And the answer is, yes, I'm sorry, dear, we ran into the bridge. But Mommy, it's okay. Mommy's okay. You're okay. But there is sort of a notion of when you're designing real-time systems, there's a real budget that you have to take care of in terms of have all these interrupts happening, all these priorities determining what's happening when. There's a lot of arithmetic you have to do to sort of make sure that everybody's happening in time. Okay. Plus, if there's any background processes. So you can imagine that perhaps playing, computer games on the space station is somewhat complicated because, the computer's often off doing other things. And we have an example here, which I don't have time to go through, which is sort of 3 tasks here: ship guidance, gyroscopes, and cabin pressure. Okay, each of which are interrupts that are important to the survival of the space station at some level. There's a scenario about how frequently they occur, that's the period, how long each interrupt takes, that's the service time, and how long between the request and the end of the service routine you have before the space station goes wonkers. So we discussed both a weak system and a strong system. I encourage you to sort of look through this to give you a real sense of some of the engineering that goes on in constructing the real-time system. So there's this slide and the next one. All the answers are here on the slide, so you can sort of work those out.